Hello everyone, my name is Damanpreet Kaur and I'm here to present my talk on seeing the invisible. A photodetector is any device which converts optical signal into an electrical one. Solar blind photodetectors are a special class of photodetectors which respond to wavelengths less than 280 nanometers of light, that is the UVC region. As we all know that the ozone layer in the atmosphere absorbs almost all of the UVC falling on Earth. This means that the background signal for these photodetectors is negligible and hence they have very high selectivity. Now, possible applications of these photodetectors include ozone hole monitoring, UV sterilization, missile tracking, etc. But perhaps the most interesting and intriguing application remains flame detection. Governments all around the world are trying to promote and develop hydrogen energy, which is a clean energy with water as the only byproduct. But this energy of the future has one major problem, which is self-ignition of hydrogen above 4% concentration in atmosphere. On top of that, another major cause of concern is that the flame is completely invisible. Here, you can see a hydrogen flame as opposed to a propane flame. Now, to image these invisible flames, you can use solar blind photodetectors. Since the background signal is almost negligible, you can easily image these invisible flames. Conventionally, these solar blind photodetectors were made on silicon, but silicon responds to visible light as well, and hence you require costly optical filters to remove the unwanted spectra. Gallium oxide, on the other hand, is an intrinsically solar blind material because it has a high band gap of greater than 4.6 electron volt. In addition, it has high chemical and thermal stability and is also radiation hardened, implying that it can be used for extreme environment applications. Now, the beta phase of gallium oxide is the most stable phase, but it requires high temperature fabrication. Amorphous gallium oxide, on the other hand, has a room temperature fabrication and can be made on flexible devices. But one of the major disadvantages remains its slow response times. We have proposed surface nanopatterning as a solution to the slow response times of amorphous gallium oxide. Here, argon ions of 500 electron volt are made incident on amorphous gallium oxide thin films, which leads to rippling patterns on the surface. Now, the PL studies show that these nanopatterning creates surface defects, which leads to faster recombination of the charge carriers, as corroborated by the TRPL studies. The surface defects induced on the surface act as recombination centers for the charge carriers, leading to faster devices. Now, these defects are also responsible for a high responsivity in gallium oxide. Thus, you can achieve both higher responsivity as well as faster devices using surface nanopatterning. This means that surface nanopatterning can be a one-step, cost-effective, simple solution to make your amorphous devices faster, leading to future commercialization. Thank you.